All right. Well, last time we went from a regular expression to a non-deterministic finite automata. Now we want to get from there to a deterministic finite automata, which we can then minimize, which we can then use to generate code for our scanner. So today we're doing that NFA to DFA step. So with the non-deterministic machine, we had all of our regular transitions, but we also had a whole bunch of those null transitions. So every time we consume, if you like, one character of input in the non-deterministic machine, we can also follow that up with a whole bunch of these null transitions. So there's usually a whole bunch of different states it's possible for us to get to when we consume one single input character in the non-deterministic machine. Whereas when we get to the deterministic one, it's, again, strictly deterministic. So you read one character, there's exactly one place where you can go next. So what we're going to do with the deterministic machine is to say, well, we'll build our DFA and say that if on this input you can get to any one of these states in the non-deterministic machine, and on this other input you can get to this other set of states in the non-deterministic machine, we'll make each state in our DFA correspond to some combination of states in the non-deterministic machine. So if we've got n states in the non-deterministic one, then there's 2 to the n possible different subsets of states in that machine. And so there's 2 to the n possible states in the deterministic machine. Now, what we're going to do is to try and use a construction technique that produces just the set of, just these subsets that the DFA actually uses. So we're going to try and, if you like, label each state in our non-deterministic machine will correspond to some subset of states in the non-deterministic one. And we'll see if we can build that up. And this can lead to quite a large deterministic machine, so that's why we're going to follow it up with a minimization step, but we'll get to that later. All right, so if we think about the example that we did from the Thompson's construction for producing a non-deterministic finite automata that corresponded to any sequence of binary digits followed by a 1, then this was the machine that we came up with, where we had a machine for the first 0, a machine for the 1 that's in that star, we had a machine for the 1, and then we built up a machine that could take the OR of these two, and then a machine that could take the clean star of that, and concatenated that with the machine that could take the 1. So we wound up with this as our non-deterministic finite automata for our regular expression. Now, what we want to do when we're creating states for our deterministic machine is to say, well, if I start in a specific state in our non-deterministic machine and I see a 0, where are all the possible places we can get to? Or if I start in a state in the non-deterministic machine, where are all the possible places I can get to? So for instance, from n2, if I see a 0, then, or if I'm going to consume a 0, I can get to n3, but I could also follow the null transitions after that, so I could also get to n6, or to n7, or to n8, or I could get from n3 to n6 to n1, which would also then let me get to n2, or would let me get to n4. So there's what, 1, 2, 3, 4, 5, 6, 7 different states we could get to on a 0 transition from n2. And so this is going to be one of the things that we have to address, is looking at reachability. If I'm starting in a particular state and I see a whatever, where are all the possible places I can get to? And it actually gets a little bit more complicated than that, because if I'm looking at my non-deterministic machine, or if I'm looking at my deterministic machine and it's got each of its states corresponds to a set of states in the NFA, then if I say, well, if I'm in this deterministic state and I see a 0, where can I get to? It's any of the places I could get to on a 0 from any of those states in the NFA. So this is what we'll walk through and look at as we try and build up our set of DFA states. So we're going to use this as our example. So I'm going to come back and forth to this. To get started, we'll have our non-deterministic machine, and we'll say its start state is n0. Remember, it's got a unique start state, and a unique end state for that matter. And we'll gradually build up a set of DFA states, and each one corresponds to some subset of the non-deterministic states. I'm going to label the DFA states, Q0, Q1, Q2, etc. as we build them. So Q0 is going to represent all the places we can get to from the start state in the non-deterministic machine with null transitions. So it's going to be n0 plus every place we can get to without consuming a character. So if we go back and take a look at that again, from n0 I could also get to n1 or n2 or n3, or I could get to n7 and hence to n8. So there's, what do we got here? 6 different states that we could get to from that starting state. So Q0 is going to correspond to that set of NFA states. As I go through and create new states for my DFA, I'm just going to add them to this set Q. So that's going to be my final collection eventually of states in my deterministic machine. And I'm going to keep track of which kind of state and input takes us to which other state. So my transition function, or my transition table if you like, is going to say, well, my transition from some state to some character is whatever. So if I'm given state Q and input C, this will tell me where I go to next. So I'm going to fill that in as we go through the algorithm. Now what's going to happen is, as we create states, we're going to have to do some processing on them. So I'm going to keep this to-do list of things that still need to be processed. So for the algorithm itself, we're going to start off by putting that start state Q0 into Q and into the to-do list. So again, that start state was this combination of 6 states I could get to from N0, N1, N2, N4, N7, and N8. So I add Q0 to Q to get things started, and I add it to my to-do list, and then I go into this while loop. And the while loop is basically saying, while there's still things I have to process, keep going. So while the to-do list isn't empty, grab the next state, like remove the next state from the to-do list, and we'll process it. And the way we'll process it is to say, okay, for each character in the alphabet, where are all the places I can get to from that state? So we're going to go back to the NFA, and remember this corresponds to a whole bunch of different states in the NFA, and say from all those different starting points on this character, where are all of the different places I can get to? And so the set of places I can get to is going to be my next state in the DFA. So I'm just going to call that temp for now. So temp is the set of reachable states from this kind of deterministic Q state. And once I know that, I'm going to add it to my transition table. I'm going to say, okay, well, from that starting state, from my start state Q to, and on this particular input character, here's where I wind up. And if this is a state that I've never seen before, then I'm going to say, I should go through and process it. So I'm going to add it to my to-do list. And I should also remember that this is one of my new states in Q. So I'm going to add it to Q. So the first time I see a state, I'm going to add it to Q and to the to-do list. So once in a while, as I'm going through this loop, I'm going to be adding new states to Q and to to-do, but not always. And every time I go through the loop, I'm going to be pulling something out of the to-do list. So eventually this thing is going to wind up empty. So what we'll do is run through that algorithm in practice. So again, let's take this same machine as our starting point. So our NFA is this one. And again, the first thing we want to do is to find what Q0 is going to be, the set of all places I can reach from my start state. So it's through null transitions. Null transitions. So it's N0, N1, N2, N3, N7, and N8. So my DFA start state, Q0, is labeled by that combination of NFA states. I add Q0 to my list of states for the DFA. So that's the only thing in it right now, and I add it to the to-do list. So again, it's the only thing in the to-do list right now. And then we start going through the while loop, each time pulling something out of the to-do list and checking all of the characters to see where I can get to from that point. All right. So let's go through that first pass where we pull Q0 out of the to-do list and see what happens. So I pull Q0 out, and then I've got to go through each of the different input characters and see where I can get to from Q0 on that input character. So this is just binary, so we've only got 0 and 1 as our possible characters. So we'll do 0 first. So I want to see what are all the places I can get to, starting from Q0, if I see a 0. So if we go back to our machine, so it was starting from any one of those 6 start states, if you like, and seeing a 0. Well, the only place where I actually see a 0 is this one here. So it's got to mean I'm doing this, I'm consuming the 0, and then I'll see where I can get to using just null transitions after that. So N3 is going to be part of my next state, or one of the available next states. N6, N7, N8, right, because I can get to all of those from N3 with null transitions. And I can also get to N1, which means I can get to N2, which means I can get to N4. So 1, 2, 3, 4, 6, 7, and 8 looks like my list. So I left 2 out of that list. Could actually get to 2. Yeah, 2 should be in there. Okay, so this should actually be N3, N6, N7, N8, N1, N2, and N4 will be my Q1. And so, again, I'm just going to call this Q1 so I don't have to keep writing this whole thing out every time I want to refer to it. So my transition function gets updated from Q0 on input 0. I go to Q1. This is the first time I've seen that state, so I'll add it to Q and I'll add it to the to-do list. And then I'll see what happens with C1. So again, this is going back and starting from that set of start states. If I see a 1, where can I get to? All right, so if I'm in that set of start states, the 0, 1, 2, 4, 7, and 8, if I see a 1, where can I get to? Well, the 2 places that actually work out are here I can get to N5, so I'll see where I can get to from N5 after I consume a 1. And there's also this one over here where I could have started in N8 and hit a 1 and get to N9. Now there's no place I can go from there, so it's basically where I can get to from N5 by nulls and my N9. So from 5, I can get to 6, 7, and 8, so that's 5, 6, 7, 8, and 9. And from 6 I could also have gone back here, so I could also get 1, 2, or 4. So there's not many places that we can't get to on a 1. I guess we can't get to N3, and we can't get to N0, but I think we can get to all of the others. All right, so our second pass, we're basically saying I can get to N1, N2, N4, 5, 6, 7, 8, and 9. Pretty much everything but 3 and 0. Again, I don't want to write this out every time I'm referring to this state, so I'm just going to call this one Q2. So my transition function, if I'm in Q0 and I see a 1, I go to Q2. So this is the first time I've seen that one, so the first time I've seen this combination of states, so I'm going to add it to Q and I'm going to add it to my to-do list. So now I've got Q0, Q1, and Q2 that I've seen so far, and I've got Q1 and Q2 in my to-do list. And the states that I've seen so far are my Q0 and my Q1 and my Q2. And so on a 0 I go from Q0 to Q1, and on a 1 I go from Q0 to Q2. So I still have to process Q1 and Q2 to see where I go from those. So we go back and start our next pass through the while loop, right, where I'll pull Q1 out of the to-do list and look at where I get to from it for each of the input characters. So if I'm in Q1 and I see a 0, where can I get to? So if I'm in Q1, which was all the places I could get to from a 0, and I see a 0, where am I going to get to? Well, again, from Q0, from my Q1, one of the states was N3, which would allow me to get to N2. So I could have N2 was in Q1. And again, this is really the only 0 in this thing. So if I consume a 0, I'm going to wind up in N3 or any of the places I can get to from N3 with null transitions, which was the N6, N7, N8. This is the exact same one that we did before, right? This is going to get us to the exact same place as Q1. It can get us to N3, N6, N7, N8, N1, N2, or N4, which was exactly our Q1. So from Q1, if I see a 0, the only places I can get to are Q1. So I'm going to wind up with an edge that goes from Q1 to Q1, right? I update my transition table to say, okay, from Q1, if I see a 0, I see Q1. Now, I already know about Q1. I don't need to add it to Q. I don't need to add it to the to-do list. So we'll just go on and see what happens if I see a 1 from Q1. So on a 1, and remember, yeah, my Q1, so starting from the same set of places, remember N8 was in Q1 and N4 was in Q1. So from those, I could have done my transition to N5, or I could have done my transition to N9, and then any of the places I can reach from those by null transitions. So I could get to 6 or 7 or 8 or 9. Well, 9's part of the my other part of this set. 6, 1, 2, or 4. So again, anything except 0 or 3. Well, again, that's just my Q2, right? I've already seen that state. So if I'm in state Q1 and I see the character 1, I can get to 1, 2, 4, 5, 6, 7, 8, or 9, which is exactly Q2. So my transition table for state Q1, if I see a 1, I wind up in Q2. I already know about Q2. I don't need to add it to my to-do list. I don't need to add it to my queue. I just need to stick in my transitions here, right? On a 1, I go from, or on a 0, I stay in Q1, and on a 1, I jump to Q2. So now my queue is still Q0, Q1, Q2. All I've got left in the to-do list is Q2, and I've updated my finite state machine, my transition tables, to say, okay, well, if I'm in Q1, I see a 0, I stay there. If I'm in Q1 and I see a 1, I jump to Q2. So now I just do this last pass where I pull Q2 out of there. Well, I guess that's a sneak preview. I know this is going to be the last pass. I pull Q2 out and see where I can get to from there. So again, if I'm in Q2 and I see a character 0, well, we know that if we see a 0, as long as we could have been in N2, which is part of our Q2, the only places I can get to are the ones that are in Q1. Right? This is the only 0 in there. These are going to be the set of places I can wind up getting. So on a character 0, I can get to 1, 2, 3, 4, 6, 7, or 8, which is exactly my Q1. So my transition from Q2 on a 0 is Q1. I've already seen Q1. I don't need to add it to the lists. And so I go on and do character 1. So for 1, again, since I'm starting in Q2 and that includes my N4 and it includes my N8, I'm going to get to any place I can get to from these on a 1, which is going to be my N9, or it's going to be that set of places I could get to from N5, which is everything except my N3 and my N0. So again, it's going to wind up taking me back to the same set of states as Q2. Oh, that should be a 2, I think. So from Q2, if I see a 1, I come back to Q2. So I update my transition table, and I've already seen Q2. I don't need to add it to Q. I don't need to add it to the to-do list. So my Q is Q0, Q1, Q2. My to-do list is empty, so we dump out of the loop. And my updated transition table tells me that my final finite state machine is this one. I've added that transition from Q2. If I see a 1, I stay there, and if I see a 0, I go back to Q1. Right, so now I've got my deterministic machine that I've built from the non-deterministic one. Now, in this particular case, we actually got lucky, and the machine that it produced is minimal machine for the expression that we're trying to recognize. Usually we're not that lucky. Usually we wind up with a machine that's got a bunch of different equivalent states that we're going to need to minimize and collapse. So what we'll do in the next session is to go on and look at Hopcroft's algorithm to actually do that minimization. I did want to mention one thing before I duck out on this, is that I keep talking about our algorithm relies on being able to grab all the states that are reachable from some state. So usually when we're playing with finite automata in terms of code, we're going to have some kind of a graph representation, either a matrix, a table of where all the edges are, which edges go, which nodes have an edge that goes from them to some other node, or an edgeless format that says, okay, for node 7, there are edges that go to this node, that node, and this node, and that might specify which character it is. Is it a null transition? Is it a transition on 0? Is it a transition on 1? But in any event, we're going to have some kind of a representation of our graphs, either a matrix-based or edgeless-based. And so we'll have a way that for any given node, we can look up which transitions are available, which transitions leave that node going somewhere else. So if we wanted to put together an algorithm to find all of the reachable nodes from any given node, what we can do is a similar sort of idea where we create a to-do list that says, okay, well, here's the possible places I can get to. Or here's the places I still have to process, and a reachable list. These are the places I know I can get to. And so what we're going to do is just keep cycling through until my to-do list is empty, and then look at what's in our reachable list. And so the way it's going to cycle through is we say from the node that I'm in right now, I look at any of the valid transitions. So if I'm looking for null transitions, for instance, then I say I look at any null transitions out of my current node, and whatever node they're going to, I add to the to-do list. Or at least I check. If they're nodes I've never seen before, I add them to the to-do list. And so what we'll do is, until the to-do list is empty, I'll just pull the front node out of the to-do list and say, where can I get to from here that's new? And so you're going through and saying, okay, well, pull a node out of the to-do list, see if there's any valid transitions out of it, so for instance, any null transitions out of it, and see if they go to some place that's not already in my reachable list. If they do, then that's a new possible destination, so I add that node to the reachable list, and I add it to the to-do list, so I can see where I can get to from there as well. And again, we just keep cycling through this until the to-do list is empty. So having gone through the algorithm we just went through for the subsets, this kind of a to-do list is reasonably straightforward to process as well. All right, I think that's where I will leave that one. Next time around, we will tackle Hopcroft's minimization algorithm.